I really appreciate the opportunity to share some of the work that I've been doing with my colleague Roger Schell, who's on the conference with us this afternoon. My name is Ed Reed. I'm with Aesec Corporation, and we specialize in providing reference monitor technology in the form of a security kernel called GEMSOS, the Gemini multi-processing secure operating system, which was evaluated by the NSA at Class A1 under the TCSec back finishing that evaluation in the 1990s. Focus of the presentation today is very much focused on what we can be doing better from a cybersecurity defense perspective. And I know that a lot of interest in industry and in government these days is focused on offense in the cybersecurity field. But our emphasis is very much on the cyber defense, and we'll talk briefly about why and how we go about accomplishing that. So with that as preamble, let me start the presentation. Oh, I should also mention that, yes, I'm an RIT graduate. I took my Master's of Science degree from RIT and the College of Applied Sciences and Technologies in the Computer Science Department, specializing in artificial intelligence and databases, and went to work after I got that work, after I finished the coursework for that. At Xerox, where I worked initially as a knowledge engineer in the one of the business units, and that's where I came to be introduced to distributed operating systems, distributed directories, the Xerox workstation network environment, and that led me to Novell in 1994, where I met Roger and also Tim Harris, who's on the call with us today, and I think Glendon Whiteley. I think all of us worked together at Novell. So here we go. How can we go about dramatically reducing the attack surface that is presented in particularly critical information systems like controllers, using integrity mandatory access controls and a security kernel? The quick outline we'll go through, but we begin with a short recital of just about how serious the problem is that we face in terms of actually a national existential risk. And we have seen, even within the last few weeks, a representation of how bad things could get with the Texas grid collapse. Now, that didn't have anything to do with cybersecurity issue, but we have also seen within the last few weeks examples of outsider intruders breaking in and actually changing things in bad ways in control systems, controlling municipal water systems. So my key message for you here today is that cyber offense is not enough. Just this week, Mike Rogers, the congressman from Michigan and the former chair of the Permanent Select Intelligence Committee in the House of Representatives, published an opinion piece in the Hill titled "Why America Would Not Survive a Real First Strike Cyber Attack Today." And in his first paragraph, he spells it out. In a full-on turn the lights off cyber war were to happen today, we would lose. That we have escaped a digital catastrophe thus far is not due to skill. It is due to blind luck and the restraint from our adversaries. That's not a strong position to be in. Leon Panetta, former Secretary of Defense and CIA Director, said, you know, this is the sort of thing that keeps the policy folks in Washington, D.C. awake at night. They recognize that a destructive attack on the national infrastructure through cyber control systems could result in the loss of millions of lives. There's been an executive order declaring a national emergency around the U.S. bulk power generation and transport system. The National Commission on Grid Resilience has pointed out that OEMs are the targets for malware that can lie in wait, and there's a cyber threat, electric sector investment needed. We have a case in point now with solar winds, of course, which has proven that exactly that supply chain is vulnerable. Washington Post had a paper talking about the bad things that would happen if the electric power grid collapsed. And I will point out to you that when we saw the Texas power grid collapse over the past month due to weather conditions, that the situation there could in fact have been much worse and came within less than 5 minutes of being much worse, because the collapse in Texas was causing electrical fires that would put out substations and relays and controlled equipment out of service for months and present a monumental problem in terms of bringing the grid back up again because of the difficulty of managing their supply and demand. What we're looking at is recognizing that computer systems all use operating systems, and that includes programmable logic controllers. We know from science that secure systems require trustworthy operating systems. You've got to be able to withstand with adversaries' cyber attacks. And if your operating system cannot stand up to an attack from the outside world, then your applications have no hope of remaining secure themselves. Current commercial PLCs use untrustworthy operating systems. None of them are trustworthy. And that's evident by the stream of regular security patches that are issued. You'll never know when the last security patch has been issued on an untrustworthy operating system. These cyber attacks have been demonstrated to be able to prevent permanent physical damage on things. Stuxnet took out a facility for refining nuclear materials in Iran. Crash override took down the Ukrainian grid. Triton tried to take out the Saudi Arabian oil production facilities. And most recently in Oldsmar, Florida, someone went in and tried to change how much lye was inserted into the city's water supply, which would have, of course, poisoned. So how do you defend against these things? How do you build a system that can actually defend itself from these attacks? The concept of security kernels has been around for a long time. It was really described for the first time in 1972, being a compact security kernel of the operating system and supporting hardware. That's an important combination, such that an adversary, an antagonist, could provide the remainder of the system, including the remainder of the operating system, without compromising the protection provided by the security kernel. That's astounding and is completely contrary to current operating system practice. In 1983, an article described this as being an approach that provide effective controls even against internal attacks. We'll describe why in a little bit, including many that the designers never considered. Why is that? Because the design of the security kernel is principle-based. It is constructed to be secure from the very beginning. It's not something you try to add on. And it has proven successful. A half a dozen security kernel-based operating systems ran for years, even decades, in environments where they were subject to outside attack, even in the face of nation state adversaries. And across all of them, there is never a reported security patch required. That's, again, astounding and completely contrary to today's operating system and application systems experience. But this is where we need to be if we're going to actually protect critical infrastructure and systems against attack and to protect customer data, even in the event the bad guy gets inside the perimeter, like happened with SolarWinds. So how do we go about doing this? In the 1970s, Butler Lamson pointed out the only way we know how to build a highly secure system is with this kernel approach. The security kernel is the hardware, the firmware, and the software elements of a TCB, a trusted computing base, that implement a reference model. We're referring to this as a reusable trusted device. Because if you can put together the hardware, the firmware, and the software to create a processing module, something that would fit on a system on a chip or onto a single board computer system, then you can provide a system that is itself inherently secure against these classes of attacks. And we'll talk about why. So you start with the hardware, you provide IO control from that hardware through a security kernel that's designed to provide the reference monitor. This reusable trusted device then can be used to support applications, security services, programmable logic controllers, and full-blown operating systems that run on top of it. This presents an entirely different paradigm for how you go about managing security and the expectations applications and service providers have to be able to make in order to how they go about allocating functionality and security to their applications and services. That's what I've done with the OpenPLC project that we'll be talking about. We use control sharing between integrity domains enforced by the mandatory access controls that the security kernel provides. So the applications don't have to protect themselves against each other. A verifiable design that's required for the mandatory access control enforcement defeats the sort of attacks that test and analysis security has sort of miserably failed. Waiting to find a problem so you can fix it is useless if you're in a first strike cyber security war. Building in the security by construction is the only demonstrated successful approach to defending against outside attacks, as well as containing insider threat operations. Now, in order to keep the system secure, you have to mitigate subversion. That means within the security enforcing aspects of the system. Sorry, I really meant to silence that. In order to mitigate against the security attacks, you have to first make sure that your security kernel and your enforcement mechanisms are actually minimized so that they don't provide any opportunities to introduce and have not introduced Trojan horses, backdoors, and those sorts of things in these security enforcement mechanisms. It's possible to do that if you build the system, construct it, so that it's secure from the beginning. But then you also have to maintain that integrity of the system security over the lifetime of the system through trusted distribution of system updates and configuration changes. All three of these things are required for secure operating systems. We refer to this as the cyber defense triad. MAC policies are required in order to secure the information flows. The reference monitor is the only known verifiable protection technology. And the system has to deal effectively with subversion, because that's the favorite attack choice used by adversaries who are able to subvert the supply chain, subvert the development process, subvert the patch distribution mechanism or the software distribution mechanism, so that the customer actually installs the malware for them. You have to design the system and the business processes and the technology around the deployment in order to be able to defend against those things. How do you do this? What in the world can you do and actually, in order to actually build a secure computer system? If you think of the universe as a collection of either secure or not secure states, then security by design begins from identifying the secure states the computer system can be in, and identifying the not secure states you don't want to let the system get into. There may be many insecure states, and there may be a multitude of secure states. The art now comes in defining the security transitions. You first have to be able to initialize the system, to boot it up into a secure state for it to begin with. From that point on, you need to make sure that nothing you do will allow the system to transition from a secure state to an insecure state. That rather carefully defines the role of this security. You want to make sure that you can transition from one secure state to another selected secure state. You need to recognize that once you get into an insecure state, it's virtually impossible to ever get yourself back into a secure state unless you start from the secure initialization to begin with. And of course, most systems transition from one insecure state to another. So the overall objective for the system designer is put the system into a secure state, only allow transitions to other secure states. That's all. That's all it takes. It's not easy. You have to begin with the definition of security. What's your security policy? Once you do that, then you can define a formal security policy model that identifies how you know which things are secure, which things are not secure. Enumerates the secure states. You cannot enumerate all of the insecure states. That's the open system world is too big and too wide to enumerate all of the insecure states. But what you can do is enumerate the secure states that are allowed for the system. And your formal security policy model has to define what those states are and the transitions that only go from one secure state to another. The formal security policy model then can be translated into a formal top-level specification for the product. And this is what we mean by secure by construction. By specifying that what you're going to build in the way of the security kernel is mapped directly to the formally proven security policy model. You can now identify whether or not your formal top-level specification is actually a true rendition, a true representation, a true instance or interpretation of that formal security policy model. And once that's been proven, you can then design the implementation to meet that. Code correspondence is the technique by which you demonstrate through mapping that your code all maps to your formal top-level specification. And because you've already mapped your formal top level specification to your formal security policy model, you know that the code that is in your system all maps to something that's required in order to support the security of the system, and nothing else. And nothing else. And it's that bit that allows you to be able to verify that your implementation have no backdoors or Trojan horses. Otherwise, your code would map to something that's not in the formal top level specification that maps the formal security policy model. At that point, you have an end product. It needs documentation, it needs a method for trusted distribution, but you can now put that product into play into an environment with documentation that explains to the local operators how to install the system, make it secure, and keep it secure. And that final end product, crucially, includes access to all of the interface provided by that processing module. In our instance, that means segmentation, because we use hardware segmentation of memory as the means for representing the objects that are going to be secured in the system. We haven't found another hardware abstraction provided by commercial hardware processors that provide the ability to describe objects in a persistent and shareable way for the reference monitor to be able to provide its protections. And so hardware memory segmentation is an important feature that has to be surfaced at the interface of the system, because that is how objects are represented in the formal top level specification, and in fact in the formal security policy model. So there are a lot of bad ways to build systems. We believe that building the reference monitor and the formal security policy model are indeed long and hard work. It took years to construct the collection of systems that have followed this design pattern in the past, and our product, GEMSYS, as well. Most people try to skip over this hard part, and as a result, they wind up with insecure operating systems, or they fail in their objective to create a secure system. Today, a lot of people tout that they have a verified operating system, which is interesting until you get around to the conversation of what is it verified to do? And the answer invariably comes back: some functionality is verified, some API protections, or other mechanisms along those lines work the way that they're supposed to work. But of course, since they weren't designed for security, they're not able to tell you anything about what the system will not do. They haven't done anything to provide assurance that there are no backdoors or Trojan horses. Their verification has simply told you what they think it will do. It's crucially important in a cyber defense perspective to know what the system will not do. Partition kernels, that was the basis for the Mills effort to define high assurance separation of partition kernels, explicitly excluded from the design of the systems of these partition kernels anything having to do with the security policy other than pure separation. But what that meant is the systems required the applications to implement reference monitors. That didn't reduce the work that needed to be done in order to create a reference model. It just meant it made it somebody else's problem. And in fact, it made every application provider's the problem of how to create a reference monitor. We think that's folly. In point of fact, we don't think that application developers, more than maybe a handful, are ever going to succeed in building reference monitors at an application level to sit on top of a separation kernel. And in fact, aside from one or two companies that have been able to make some money selling things to the DoD, they haven't. Not a general purpose solution, not something that could be applied to control systems or the general problem of how to protect cyber physical systems, or for that matter, IT systems from hostile attack. We have seen folks try to create verified capability hardware using things like FPGA and technologies along those lines. And again, those folks are missing this whole concept of what do you mean secure? They want to provide the stuff that you could create a secure thing with, but they want to leave that hard part of defining the formal security policy model to somebody else. Not helpful. Static code analysis, wonderful techniques. Love what it does in terms of improving robustness of applications. Does nothing to talk to about the security of the system. I don't want to play it down. I think it's a valuable tool. I just don't think it gets you security. What it does is get you more robust applications. That's a good thing. Use those more robust applications on top of secure operating systems. So these shortcuts cannot enforce integrity MAC for PLCs. So what is it that we're trying to do here? When we talk about reducing the attack surface, start with a physical device. Here we have, I don't know, it's a generator or a fan or some moving physical thing that needs to be controlled. If you want to be able to control it, you're going to probably attach it to a public network. Whether you intend to or not, you are. You may be doing this using TCP/IP. You may be using this doing serial ports. But in any instance, you're interacting with the public and the public networks that are out there. And you may be running a large protocol stack within your environment that itself presents an attack surface. So maybe you put another domain within your system that is all about managing distributed control. This might be a mechanism, a means to be able to securely connect between two machines. Application-wise, you might think that looks like SSH or HTTP secure, but there are real problems with trying to do things like security at the application level. Then you get to the whole notion of SCADA itself. How do you go about seeing to it that the control device remains within the appropriate parameters that are set for its operation, that the logic is correct? And you see, each time we add another domain here, we're reducing the circumference of that circle and reducing the attack surface on those pieces. But most importantly, there's some place in the system that is actually interacting with the control device. And if we can confine the attack surface available to an attacker to that piece which is specifically responsible for sending commands to the device, we can dramatically reduce the code footprint, for example, that's available for attack in the application space. Now, applications can't do this, but if you put applications that build that framework for programmable logic controllers on top of a secure operating system, it becomes possible. OpenPLC is an open source project for delivering programmable logic controller application running on Windows or Linux. We've looked at how we could go about implementing OpenPLC on Gemsons, our security kernel. NIST, the National Institute of Science and Technology, calls out this notion of a kernel in their SP 800-160, talking particularly about how industry should be looking at applying this kernel notion to electric grid and industrial and process control systems. If we can build those industrial control systems on top of the secure operating system, then the kernel MAC controls, the mandatory access controls, protecting the integrity of the kernel itself and of the data that is under integrity protection on the kernel, can dramatically increase the system integrity and its applications. So what does that look like? This diagram is too dense to try to go into any great deal of discussion here, except to say that we're using the Intel architecture's hardware rings of protection, all four of them, and mapping aspects of the security kernel and aspects of the security services, and then the more general operating systems to different privilege levels. So we are using the hardware protection mechanisms to protect the operating system from the applications, to protect the security services from the operating system, and most importantly, to protect the security kernel from everything else. Then we can use different security domains for the public networks, for the distributed control, for the SCADA, the cyber physical control. And that has the effect of creating a very small attack surface for the cyber physical control compared to the very large attack surface of those public network environments. We are using 4 hierarchical integrity domains. 1 for that cyber physical system, 1 for the SCADA, 1 for the distributed control, where you need a trusted path between your human machine interface and the PLC itself, and another for the untrusted network over which it all runs. OpenPLC was developed first by Tiago Alves in Brazil. He continued development on it as a student and a PhD student at the University of Alabama in Huntsville, working with Tommy Morris. And it really presents a highly functional PLC capability designed to run on Windows and Linux. And some commercial vendors are using it. We've been fortunate enough to work with Matt Bishop out at UC Davis to install a version of GEMSOS in their security lab on which we've installed this demonstration. For the propeller heads in the conversation, getting a sense of how the data flows from, for instance, a TCP connection coming in through an internet device, cascading through cross-domain services into the SCADA domain, where operations against the Modbus database are mediated using mutexes with the program logic, which itself is running its own loop in connection with gathering data from and sending commands to the process that is actually controlling the physical device. I would be delighted to, and probably would, spend a lot more time discussing this if we have an opportunity for a follow-on discussion. But just looking at the code size involved with these things, just looking at the executable statements involved, and here we're actually counting as assembled and linked instructions. You can see that public network is monstrously large. SCADA is actually very large itself, but it's hidden behind 2 layers of hardware protection. But that cyber physical control, reducing that attack surface to less than 1%, really is a substantial reduction. So this mature approach to mitigating subversion that's available through the Class A1 technologies is why NIST cited Class A1 in their SP 800-160, as it is looking to try to persuade industry and researchers to use this type of technology as the secure operating system below their other more ambitious applications. We have a number of products that are worked examples. They're highly resistant to penetration. And TCSec Class A1 itself is distinguished by the way it addresses the issue of subversion. The device protects itself. There's a trusted boot to get the system into a secure configuration. Devices are vetted so that you know when you plug them in whether or not the devices could have been hacked and how it's controlled in case they were. Here we're talking about storage devices, network attached devices, graphic adapters, things like that. Code correspondence stops the dead code malware. Trusted distribution prevents introduction of attacks to the supply chain. And media integrity mitigates against parking lot attacks. And by that, you probably know that one of the ways they bypassed the firewalls in the Iranian nuclear processing facility was dropping thumb drives in parking lots that when you plug them into a computer behind the firewall, infected that computer and then searched out across the network for other computers that it was looking for, in particular process control networks. This is a representation of what a sophisticated supply chain trusted distribution scheme looks like. And it has some important characteristics. The integrity of the security kernel is distinct from the integrity provided by the application service providers. They don't both rely on the same cryptographic mechanisms. But the trusted device is responsible for providing those cryptographic mechanisms by which the vendor's applications themselves are trustworthy. So I have a very short demonstration. And this falls in the category of how do you make security, which is as interesting to watch as watching paint dry, something a little bit more entertaining. And that is by adding blinking lights. Welcome to the second demonstration of OpenPLC on GemSys using multiple high integrity security domains in order to reduce the attack surface available to attackers. This demonstration is using the classic traffic lights exercise for programmable logic controllers. Implemented on a breadboard, wired to an Arduino microcontroller, connected via RS-232 to GemSys, and then the other GemSys RS-232 port is connected to a Modbus master application running on Windows 10. The cycling of the lights for the two traffic light configuration you see here is being controlled by a logic program running on GemSys, making use of system timers available through the GemSys interface, used by the OpenPLC software to implement the timer function blocks. And you'll see that the lights cycle through the familiar red light transitioning to green,
transitioning to yellow before transitioning to, that's a yellow light. I'm missing an LED, the second yellow LED. I'm transitioning back to red again. And so the demonstration is working. I express my appreciation to the folks at the University of Alabama in Huntsville who provided me with the logic program for the traffic lights, so I didn't have to figure out how to program that logic myself. That concludes the demonstration.
And so, yes, even watching paint dry can be entertaining if there are blinking lights. So once again, cyber offense is not enough. You've got to provide high assurance cyber defense. And right now we're not. We know how to. We can use a reusable trusted device providing a reference monitor implemented through a security kernel in order to host operating system services and application services like programmable logic controllers, as long as the product also provides mitigation against subversion. And we gave our demonstration. Critical physical components need a verifiable PLC. The kernel makes cyber physical attack surface much smaller. The security kernel's verified design allows it to provide integrity mandatory access control domains and protect them even against unknown attacks. It also has to deal with subversion of the security mechanisms. And then the PLC performance and functionality can be retained with even open source software running on top of this trusted device. This is that crucial difference between us and those folks who would tell you you really just need separation, for instance. If you don't have the reference monitor in your operating system, then you have to have very expensive applications. But if you put the investment into the operating system for the security kernel, it will provide the high assurance integrity and the high assurance secrecy protections that you need to let you run even open source software, like we're doing with OpenPLC. And that's it. I have time for questions if there are any.